So we're looking at questions from lesson 7. You asked number 6. I like number 6. In fact, you know what? I love number 6, and that's no April Fool's joke. You're going to see it. So much so that I'm going to actually move down here and draw it down here. So here's what we have. We have, if I'm reading this question correctly, two parallel plates. I'll cheat and use my line function. So there's one. There's the other. And what's the voltage between them, Pat? What did the question say? So I'm going to go 250 volts on this side and 0 here. Just I want to visualize this. And what charge are we moving? A positive or a negative charge? A positive. So that must mean it's starting here, and it doesn't want to stay here because this is positive and this is less positive. I can't really call it negative because it's 0, but it's compared to this, it's negative. It wants to move to the right. In fact, I would argue, Pat, that this is the same as dropping an object down to the earth, mathematically. What type of energy does this have before you drop it? What does the potential energy turn into? Kinetic. At the very bottom, how much potential energy will it have? 0. It will all become kinetic. What we're going to say is this. Potential initial plus kinetic initial, this is number 6, right? Equals potential final plus kinetic final. But what I'm going to argue here, Pat, and I might even jump to this right away, is I'm going to say, look, it has no initial kinetic, and once it moves all the way across the voltage, it's hit the ground, so to speak. Okay? And it's going to give us a lovely equation. It's going to give us a half mv final squared. This is electric potential energy, so I'm using MGH. And I can't use the K, Q1, Q2 over R because there is not two charges in here. What's the other equation on our formula sheet, which we might want to have out in front of us as a little handy reference, by the way, that has potential energy in it? And if we're lucky, maybe it even has potential voltage in it. I'm going to write it this way, though. Q, V, and Pat, this is really the equation where my prof introduced the wings, because this is the equation that has two V's almost side by side. So capital V voltage, little v velocity. Do I know the charge? Do I know the voltage? 250. Did they tell me the mass of the particle? I hope they did. What was the particle? Was it a proton or was it... Okay, or they'll tell you the mass. So proton is from my sheet, charge is from my sheet. As it turns out, it looks like V final is going to be this. 2Q voltage over the mass square rooted. In fact, this one is clean enough that I did get the V by itself before actually plugging in the numbers, which I haven't always done in this unit, but that one I could. I like this, Sally, because this is dropping an object and having it hit the ground mathematically, but sideways and with completely different forces in a situation. But it's the same concept. All of your potential becomes all kinetic just before you hit the ground. I kind of like that. And also I like it because you're probably going to see it somewhere in the future. Okay? Now, when we talk about how a television works, what we're going to do is we're going to put a very tiny slit right there so that it can fall through, and that's how you accelerate protons or electrons to speed. Electrons is easier. Does that make sense? And when you see it, like, oh yeah, pretty good. Any others? Sure. Getting close to being done, nearly there. Then let's look at lesson 8, which is a continuation of parallel plates. Lesson 8. And Pat, I'm kind of glad you asked this question because it's going to be a great segue into today's lesson, because today's lesson is looking at parallel plates and energy problems, strangely enough. In fact, we're going to formalize what I just showed you in question 6, among other things. So, for parallel plates, the voltage is merely given by the battery that it's hooked up to, and it varies directly with the distance between the plates. We've said that already. We recall that for a test charge placed at a point whose voltage is known, we can find the potential energy using, well, we said this. We defined voltage as how much energy per charge there was at a location. That must mean that if I get the potential energy by itself, hey, look at that, Mr. Walkowski. QV looks familiar. Okay. And this one here works both for point charges and for plate charges, because how many charges are there in this equation? I only need one. If I have two, great, if I know the voltage at that location. Or if I only have one, as long as I know the voltage between the plates, great. Example 1. Find the work done by an external agent, or invisible angels, that move a positive 2.5 microcoulomb charge from the negative plate to the positive plate. Assume the charge begins and ends at rest. First of all, which way does this positive charge want to move, up or down? Down. This is the same as lifting something off of the earth, except instead of gravity, it's electrical force. So, are we changing the height? Yep. What's this question wanting us to find? Work. So we're going to fall back on our work equals change in potential plus change in kinetic. Although, Evan, if you didn't bother writing this second term, it wouldn't bug me, because doesn't it say that this charge begins and ends at what? Rest? If you left that off, I wouldn't freak. I'll put it in our notes, though, so that we remember it. That's the overall equation, and then we modify it. What's changing? Anything? Final minus initial? Yeah, I'm really getting why you hammered that, Mr. Duke. So this is going to be the final potential energy minus the initial potential energy, where potential energy is going to be Q V final minus Q V initial. However, Connor, starting out here, what's your initial voltage? What's your initial potential energy? You're on the ground. And again, I keep trying to go back to gravity because we're familiar with gravity. We can visualize things dropping. So, that. In fact, if I want to find how much work, it's going to be the charge times the voltage. Bigger charge is tougher to move. Oh, it's like bigger mass is heavier to lift. Tougher to lift. It's going to be 2.5 times 10 to the negative 6 times 120 volts. 120 volts is roughly what comes from our power outlets. This is actually sort of what's going on when you put a rechargeable battery into a recharger. The voltage from the outside is forcing positive charges to go where they don't want to go in a chemical reaction, and they get stored there. And that means, Jordan, they have energy. Then when you hook that battery up to a device, they fall, they lose that energy. Where does it go? Not into kinetic, it goes into electrical energy powering the device. Okay, so that's what's going on. Except I've totally lied, because is it really the positive charges that move? No, but you know what? Moving negatives down is kind of the same as moving positives up. So, yeah, good analogy. What'd you get? 3 times 10 to the negative 4? Why would this be incorrect? Yeah, and be really careful on your test. I have a specific question in mind that works out almost evenly, and kids always forget to go to 2 sig figs or 3 sig figs. So please check. Example 2. Here we have an electron beam. And we're starting out touching right over here with a speed of 0. And we're going to shoot it through some parallel plates. But this is actually how you build an electron gun, also called a cathode ray tube or a cathode ray. An electron gun, if you put a very small slit between the parallel plates, you'll have the electrons coming out roughly in a straight line, because anything that's going sideways hits and collides. If you have a really, really small slit, basically things can only come out in a straight line. So, how fast? This is number 6. How can I tell that this is not a work question? Did they ask for how much work? Did they mention some kind of external agent or something doing the work? Nope. But there is a speed and a change in height. I know it's sideways, but there is a speed and a change in height. Energy, conservation of energy. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Okay. Now, this is charged negatively. This is 0. The author does say, by the way, this would still work if you had this 0 and this positive 125, because even though this isn't negative compared to this side, it would be. The electron would still want to move to the most positive section. Are any of these 0? Yeah. So this is a bit of a twist, Ryan. It's falling to the ground, but I guess you can imagine we've dug a hole in the ground so it can keep falling. Except in real life, it would continue to speed up because it would there be. We're going to pretend that it doesn't continue to speed up. So my analogy breaks down again, but still, potential energy between plates, Q, V, a half m little v squared. And you'll notice, Regan, the nice thing here is I haven't had to tell you how far apart the plates are. It doesn't depend on that, which when you're building televisions means you have some flexibility, which is nice. What you don't have much flexibility in TVs is your source voltage, because you're plugging into a plug. It's all coming out at 120 volts. So you'll need either some kind of transformer or step-up amplifier or something like that if you need more volts, and usually most TVs need more volts. I'm pretty sure, correct me if I'm wrong, V is going to be, move the 1/2 over, it becomes a 2. The Q and the voltage stay, and you would divide by M and then square root. I think that's right. Yep. Hey, let's crunch the numbers. Big square root sign. 2. Uh-oh, they didn't tell me the charge. Or did they? Yes, Megan, it's an electron. They never need to tell me the charge. And some of you may already have it memorized. What's the charge on an electron or a proton? 1.6 times 10. Voltage. 125. Oh, by the way, you could argue that it's a negative charge and a negative voltage, and you'd have negative times negative, because Mr. Dueck did say for scalars, put in the sign. Here's what I said. Am I taking the square root? Do I need a positive number in my square root to make it? Then it's positive, please. Mass. Electron, I know it's 9.11, but I can never remember the exponent. Is it times 10 to the negative 31? Ooh, I'm finally getting that one. By the way, what's the fastest objects can travel in the universe? Speed of light, which is on your sheet and a built-in error check. If you get an answer bigger than the speed of light, you've probably forgotten to square root. It's the most common mistake. And it's not like I haven't yelled at you at all this year about squareds and square roots ever. What do we get? Don't all rush for your calculators at once, Justin. 6.6 times 10 to the 6. Anybody else? And that sounds about right. Usually I find for voltages when we're moving, especially electrons, because they have so little mass, they hit 10 to the 6th or even 10 to the 7th. 10 to the 8th, you're approaching light. Probably made a mistake, but 10 to the 6th, 10 to the 7th. Is it 6.6 times 10 to the 6th? Pretty fast. Really fast. So, as we see in the above equation, when a particle is accelerated from rest, so it has no initial kinetic, we have a simple energy equation. All of the potential becomes all of the kinetic. However, we must take care in this equation not to confuse the V with the V. Well, it's technically a change in voltage, by the way. But the reason I don't say what's a change in anything final minus initial, we can glance at the picture and figure out the change in voltage in our heads always pretty easily. So I figure it's kind of a waste of time to write that in. But I should say, yeah, okay, it's because you're changing voltage locations. That's what you're gaining or losing your potential energy. An electron, turn the page, already moving at 5 times 10 to the 5th meters per second, enters a set of accelerating plates. Find its speed when it leaves the plates. So what they've done is they've drilled or put a very, very tiny hole in this set of plates and a very, very tiny hole in this set of plates. So this electron is going to come here. Compared to the right side, is the left side positive or negative? Negative. So as soon as the electron gets here, it's suddenly going to get repelled and attracted. This is going to be like a huge turbo boost on your video games. Pshoom! It's going to speed up, and it's going to leave out the other end. How fast? Okay, now my initial kinetic isn't 0, so I'll fall back on kinetic initial plus potential initial equals kinetic final plus potential final. Are any of these 0? Okay, when it gets to the far end, it's fallen to the ground, so to speak. I don't think any of the other ones are, so let's plug them in. A half mv initial squared plus qv equals a half mv final squared. Do the m's cancel? Not this time. It's not gravity we're dealing with here. I think I'm going to get this left hand as an answer, and then I'll move the 1/2 and the m over and square root. So I'm going to go 0.5. It's an electron, 9.11 times 10 to the negative 31. 5 times 10 to the 5th squared plus 1.67 times 10 to the negative 19. What's the change in voltage that it's traveling through? This is why I said I don't write delta V, I just do it in my head. How many volts is it traveling through? Not 600. How many? 500. That equals a half mv final squared. .5 times 9.11 times 5 times 10 to the 5th squared plus 1.6 times 10 to the negative 19 times 500, double check my typing, a half times the mass times 5 times 10 to the 5th squared, 1.6 times 10 to the negative 9. That looks good. I get 8.011 times 10 to the negative 17. 8.011 times 10 to the negative 17 equals a half mv final squared. So Ryan, I'm pretty sure that the final speed is going to be 8.011 times 10 to the negative 17 multiplied by 2, because that's the same as dividing by a half, and divided by the mass, which is 9.11 times 10 to the negative 31, and then I better square root that puppy, otherwise I'm going to be faster than light. So I have this number stored in my calculator, times 2 divided by 9.11 times 10 to the negative 31 Enter. Square root. Oh. 1, 2, 3, 4, 5, 6, 7. And Sally, it's 10 to the 7th, bigger than the previous one. But was it moving to begin with? Oh, you know what? It should be bigger. I think I'm okay with that. I think, and it's a bigger voltage as well. So 1.3 times 10 to the 7th meters. Whoop! Wow. Meters per second. So let's talk about how a TV works. Okay. A cathode ray tube, a CRT, is a cathode ray tube. And in the simplest cathode ray tube, a beam of electrons, so you have a very, very negatively charged plate, actually a coil of wires. You're sending a big negative charge through it, Justin. And what you also do, although I'm not going to include them in the diagram, is to force them into a straight line. You put a big negative plate right there. Don't write this down. It's going to clutter up your diagram. And you put a big negative plate right there. And what those both do is they push. They repel the electrons. If the electrons are being repelled from the top and the bottom, where will they end up? In the middle, in a nice straight line. Okay? More expensive televisions back in the day had better systems, better hardware. And what you do is you have this charged negatively and you have this charged positively, and you get a beam of electrons. Just so this here is just like the diagram right above it. As the electrons come through, you have some deflecting plates. The top is positive, the bottom is negative. So as the electron travels through here, it gets pulled up a little bit because the positives attract and the negatives repel. And so it hits the TV, the back of the TV screen, right there. And what you have is the back of the TV screen is coated with a fluorescent paint that will fluoresce, glow, when it gets hit by one electron. That's how black and white TV worked. All you were seeing from the front of the screen was electrons causing the paint on the interior of the television screen to fluoresce. Oh, and then they got really clever. Sally, the deflecting plates, what they did, they hooked that source voltage up not to a battery, but they hooked that up directly to the camera. So the voltage that you're getting is directly proportional to the image that the camera is picking, which means that it would naturally, the voltage would naturally take care of itself. You didn't have to do any math, you didn't need any computers, it was all analog. The voltage here would naturally recreate the image because the voltage coming in was directly proportional to the image coming into the camera. Beautiful system. Except my diagram isn't great. Let's see if I can show you a better diagram. Is this the one that I want?
How does the monitor work?
This one first.
But there's still something I don't understand, Mr. Whoopi.
Well, what's that, my boy?
I looked real close, and I didn't see any picture going across the room between the camera and the TV set.
But of course you didn't. There wasn't any picture, just electromagnetic waves which are invisible.
But then how?
How does it get to be a picture again? Well, let's go back to the 3D TV. Inside every TV set, there's a big tube. You call it a picture tube, but the correct name is cathode ray tube. It takes the waves from the transmitter and turns them back into electrons. In the back of this tube, there's an electron gun which shoots the electrons at the front of the tube. The front of the tube is coated with a special chemical which lights up when the electrons hit it. And this is what makes the picture.
I get it. The orthicon tube turns the picture into electrons, and the cathode ray tube turns the electrons back into the picture.
Precisely, my boy.
I couldn't resist the cartoon. Not a clear explanation. A much clearer explanation is right here, but I still couldn't resist the cartoon.
How does the monitor work? Signals from your computer's video card are loaded into 3 electron guns at the base of the monitor.
Now this is color TV. So black and white TV only had 1 electron gun. Color TV has 3 electron guns. One's going to give you reds, one's going to give you blues, and one's going to give you greens. And the interior of the television is actually coated with, I think, 3 different types of phosphorescent. Watch.
There is 1 gun for each of 3 colors: red, blue, and green. These 3 colors, when mixed together, can create all the colors you see on your screen. Now, these guns don't shoot bullets. Instead, they shoot a powerful beam of electrons towards the face of the monitor. The beams pass through the deflection yoke. It uses magnetism to bend the electronic beams so they can sweep across the entire screen and create the picture we see.
What happens once the beams have swept your monitor? Special chemical phosphors are painted on the inside of the monitor. Energy from the electron beams makes the individual phosphors glow either red, blue, or green, depending on the type of phosphor. The stronger the electron beam, the brighter the phosphors glow. A sheet of metal with holes in it helps keep the electron beams aligned exactly with the phosphors. This is called a shadow mask. The beams sweep across the entire screen 60 times per second. It happens so quickly that you are unaware of the firing process.
60 times per second, 60 hertz. You may have heard that televisions have frequencies. Now the newer, expensive ones, I think you can get some now that are 120 hertz. I don't think they make much of a difference because your eyes can't spot the difference. They're just charging you more money.
Instead, your screen appears to be a steady, continuous image, just as it does now.
So there is the cathode ray tube. So it says, describe the motion of an electron beam in a cathode ray tube. The electron is deflected up or down, and we can deflect it down just by reversing the voltage, which conveniently is why we have one of the benefits of having alternating current. The electron is deflected up or down and hits the fluorescent, spelled it wrong, did I? Fluorescent, there we go, screen, producing a glowing dot. We call them pixels. This is not how the flat screens work. This is not how the LCD or the plasma or anything or the retina display works. But this worked great for about 50 years. It was low tech. It was analog. Worked wonderfully. Can you see though why your TV screen never looked quite like real life? First of all, you were limited to dots, to pixels, but even you can't quite get the electron beam perfectly straight. There's always going to be some bleeding on either end. Example 5 is nerdily cool, but we're going to pass. We're done the unit. All I'm going to be doing for lesson 9 is review. So your homework, number 1, number 2, number 3, number 4, 5 is good, skip 6, 7 is good, 11 is good. I'll pause there. It's a short day. Okay.